We have here two pieces of code that are attempting to calculate or approximate the average of data in an array. The first piece of code takes each item from the array from index 0 to the array's full length. It sums them, and then it divides by the size of the array, by the number of items that it summed. The second one approximates the average from that array by taking half the data. It goes from index 0 to index array length divided by 2. It sums those items and then divides by the number of items that it summed. So the question that I have for you is whether these two algorithms have different big O complexity. Do they fit into different complexity classes? Or in other words, thinking about how they grow in relation to the size of the array, do they grow by different categories of patterns, by different big O patterns? Why do you think that, or why do you think they do not? So pause the video for a moment and think about whether these algorithms have different big O complexity. You may be starting to get enough of a feel for complexity classes that you might have caught on that typically when you see a for loop that goes from 0 to the length of an R data that does something, a single thing or a couple of things in there, that's going to be linear. So this first one is going to fit some linear pattern. It's going to be O of n, because these things are constant, this is constant, but this for loop will go from 0 to n, the length of our array. The other one might be a little trickier for people. So it has some constant portions that are the exact same as the previous version, and it goes from 0 to something. The question you have to ask yourself is, does this number that it uses for its stopping criteria grow in the same pattern in relation to the size of the array? So this one was something times n, and this one is going to be something times 1/2 n. And anything times 1/2 n is still going to be a linear pattern to it. So let's say it was 3 times n up here. It typically is for these sorts of simple for loops, depending on whether you count plus equals as one operation or two. It's probably about 3 or 4 n. Well, this one will be 3 or 4 times 1/2 n. That would give us about 2n, which is a different amount. And maybe if you had to choose and your users were okay with an approximation, this may still be an okay choice. But what it doesn't do is it doesn't escape from the complexity class that you were stuck with above. So if you were worried about having something that was O of n, which this is, then you're going to be in as bad of a situation down here because it will be O of n as well. It will be 1/2 something n, which will also be O of n. So it'll be something like 0.5 times something times n, which gives us O of n. And this one is just something times n, which also gives us O of n. If we wanted a different category of behavior, we would need to make sure that what we were doing was in a different scope and didn't grow in the same way related to the data. Here's one example of how we could do that. We could make an average of 3 of the items from the array. Now, this 3 will not grow or shrink depending on how big my array is, as long as it's more than 3 and I don't get an error from this. I should probably do checks for that, but I'm not going to for this example. This, however, would fit a different category because you could give me 1,000 items and I will average 3 of them. You could give me 7 items and I will average 3 of them. You could give me 5 million items and I will average 3 of them. It's a terrible approximation, probably in most cases, but it's going to be something times 3, and that something will be a constant amount, 3 or 4, depending on how we count the steps in this array. And so this will be O of 1. It's a different category. And so if we were concerned about our data growing very, very large, optimizing like this half approximation is not really going to get us out of that fear, because once our data doubles from whatever number we were worried about, let's say we were worried about when we hit 1 million users or 1 million sales that we're averaging the prices of. Well, once we hit 2 million sales, this one is just as bad as what we were worried about, because it will be averaging 1 million of those items, and it will be just as slow as when we were worried about 1 million items. So if our data is growing, which much of the data that we deal with day to day in programs does grow large, then this doesn't save us. It keeps us in the same complexity class. And this is often true with optimizations people notice. Maybe they notice that I could skip one of the operations that was happening in here. That's great, and that could be a good optimization, but it doesn't escape the growth pattern. Only finding a different category of behavior, finding a way to do this in logarithmic growth, or finding a way to do this in constant growth like I've shown here, constant is no growth, those will save us from constantly expanding data, and data that's growing and growing and growing into sizes that become unmanageable for something that is, say, O of n or O of n squared or something large like that. So we can do little optimizations. They will not necessarily change our complexity class. We have to think about what is growing in terms, or what operations are growing in relation to the data, and see if we can change the pattern. See if we can change the pattern to one that is constant or is logarithmic. We won't always be able to, but sometimes we can, and we should choose the algorithm. We should choose the approach that puts us in that best growth category, so that as our data increases, then our time that our code takes to run will not increase at such a drastic rate. And you will look at the example of search and finding items inside of an array, for instance, in your activity for today, as you look at Model A from the search activity.